Hi everyone. In this video, we'll look at some more theorems about convergent sequences, as well as introduce a new type of sequence called a Cauchy sequence and look at some properties of Cauchy sequences. So we want to begin by looking at two theorems related to convergent sequences. So the first is something called the monotone convergence theorem, which says that if AN is a bounded increasing sequence, then AN converges. Now, before we prove this theorem, we can think about a few properties, right? We sort of know there's boundedness. We now have, increasing, which we can think of as being that sort of a special case of monotonicity or being monotone, right? So, and we have convergence, right? And we've already seen, for example, in the previous video that all convergent sequences are in fact bounded. And we could start to wonder, do any of these imply the other, right? So, and it's nice to build up some examples in your mind, like even if these don't work, to know what the counter example is, right? So you might wonder, is every bounded sequence convergent? Okay. Well, no, right? If I just take the sequence A sub n is -1 to the n, right? This is bounded, but not convergent. Okay, so we see that that arrow can't go in the other direction. Just being bounded is not enough to prove convergence. Is monotone enough to prove convergence? So if that's a no. If I take an is equal to n, this is increasing, but it's not convergent. You could wonder if convergence might imply monotonicity, but of course that's also not true. So if I take -1 to the n over n, so as n goes to infinity, this numerator is bounded. The denominator is running off to infinity. So this, as n goes to infinity, this will converge, but it's not monotone because of this alternating sign. Okay. You could, of course, wonder if either of these imply the other, right? So certainly monotonicity does not imply boundedness. So, right, could add that on here. So this is not convergent or bounded. Does bounded imply monotone? Well, no. Okay. And so I think we've covered all the possible scenarios here of one of these properties implying the other. So the only one that really works here is that convergence does imply boundedness. All right. But then you can start to wonder, what if I package a couple of these together, right? So would convergent plus bounded imply monotone? Well, of course, that's not, if it's convergent, it's automatically bounded. So that's really the same as asking, does convergent imply monotone, to which the answer is no. So convergent plus bounded does not imply monotone. Does convergent plus monotone imply bounded? Well, of course it does, because convergence on its own was enough to imply boundedness. Okay. And so really the last question is, well, what about monotone plus bounded? Does that imply convergence? And this theorem actually says yes, right? If your sequence is again, we've stated it here as increasing, but you could just as easily come and replace that increasing with monotone. Then you can say that these two together do imply convergent. Okay, so let's step through that proof. So I'm going to start with a sequence which is both monotone and bounded, and I want to prove that it converges. Now, the only way I can prove right now that a sequence converges is to have some candidate for the limit. Okay. and then show that it actually does converge to that thing. Okay, so of course I want to prove that something converges, so I'm going to need epsilon greater than 0. And now I need a candidate for my limit. Okay, well, what's happening? This sequence is increasing. That's what I think about visual. This sequence is increasing, but it's also bounded. Okay, so somehow the idea is it's got to be leveling off at something. And how do I describe that? Well, it's leveling off sort of at some sort of bound, but like it's not just any bound, right? Because there's an upper bound. Maybe I want it to be sort of the smallest of all the possible upper bounds. Well, we have a name for that, right? It's the least upper bound or the supremum of that set. So let's set L to be the supremum of the set E, where E, so I want to be a little careful here and explain what I'm talking about. So AN is a sequence. Sequences are ordered. Okay, so for example, I could have a sequence AN, right, which is 1, 2, 1, 2, 1, 2, and that makes perfectly good sense as a sequence. The set E is going to be the set of all the outputs of the sequence. So here the set E, remember, sets don't care about order. There's no order. They just care about the values. So the set E would just be the set 1, 2, right? It's just the set of all outputs of this sequence. And of course, as a set, that's the same as 2, 1, right? Order doesn't matter for a set. Okay, so what I'm going to do is I'm going to define this value L to be the supremum of all of the possible outputs of my set. All right. Now, since L is the supremum of this set, okay, then there must exist some element of my set E. I'm going to call it A sub capital N, such that A sub n, A sub capital N, gets greater than L minus epsilon. Okay. Now, why does that have to be true? Well, if there were no element of our set E, which got bigger than L minus epsilon, what would that mean? That would mean that every element of our set was less than or equal to L minus epsilon, which would mean L minus epsilon was an upper bound for our set. But L minus epsilon can't be an upper bound for our set because it's smaller than L, and L was the least upper bound. Okay, so I have to be able to find an A sub n between, it's certainly going to be less than or equal to L, but it's going to be greater than L minus epsilon. Okay, but this is equivalent to AN minus L in absolute values is less than epsilon. So to see that, move the epsilon over to this side, move this over here, you would get L minus A sub n is less than epsilon. But remember, or sorry, A sub capital N. But remember that this is the supremum of this. So this difference is always positive. And so you can just slap absolute values on here and swap the order, and you get this condition here. Okay. And sorry, this should be a capital N here. So what we've done is we have found one specific element of our sequence that is within epsilon of L. Now I'm going to argue that all the subsequent ones are also that close to L. So this is where I haven't yet used the fact that my sequence is increasing. But since A sub n is increasing, for any little n greater than capital N. So these things are increasing, right? So as I move up beyond a sub capital N, I go to a sub capital N plus 1, a sub capital N plus 2. Those all have to be bigger than a sub n, which means they're getting closer to L. Less than or equal to, but this is strictly less than epsilon. Okay. But notice what we've shown is that for any epsilon greater than 0, there exists a capital N such that whenever little n is greater than capital N, a sub n minus L in absolute values is less than epsilon. Hence, we've just shown here that a sub n converges to the value capital L. Okay. So really what this theorem allows you to say is that if you have a bounded increasing sequence, or more generally a bounded monotone sequence, you know your sequence will converge. Now, what will it converge to? Well, if it's increasing, it will converge to the supremum. If you actually change this from increasing to decreasing, then you just change to infimum here, and you need to take a little care to flip some inequalities in appropriate ways. But everything still works out so that you get it's a convergent sequence. So this is a nice theorem because it's the first theorem we have that allows us to prove convergence without actually having the candidate for what it converges to. Although in some ways, even saying that is a little disingenuous because I know what it's actually going to converge to. It's going to converge to the supremum. It's just that, well, I might not need to bother calculating what that supremum is, right? I just know that whatever it is, it will exist because I have a bounded set of real numbers, a non-empty bounded set of real numbers. So I know it exists. I just don't need to bother calculating it in order to know that my sequence converges. All right. Now, the next theorem we want to look at actually has to do with subsequences, right? So we might wonder, so we had this sort of, does boundedness imply convergence? And the answer was no. But what we actually know is that boundedness won't give you a convergent sequence, but you should be able to pick out a subsequence that is convergent. So another sort of way we often see this theorem stated is that every bounded sequence of real numbers has a convergent subsequence. We'll talk about how we get there from here in a bit, but just as a starting example, right? If I think about something like this is a bounded sequence, right? This sequence is just -1, 1, -1, 1, so on and so on. It doesn't converge, right? But I could go through and pick out, for example, all the odd terms, right? And I would just have a sequence of -1s, right? And that converges obviously to -1. Likewise, I could go through and pick out all the even terms, right? And if I picked out all the even terms, I'd get a sequence of just ones. That obviously converges. So even though this sequence doesn't converge, it has subsequences which are convergent. Now, I could do this in other ways, right? So I could take something, say, like n minus 1 over n times -1 to the n. Okay. So if I start writing out terms of this, my first term will be 0 when n is equal to 1. When n is equal to 2, I'll get 1/2, and I'll get -2/3. Then I'll get +3/4. Then I'll get -4/5. Then I'll get 5/6, -6/7, +7/8, so on and so on. Okay. Now, again, if I look at sort of odd versus even terms here, right? If I take the odd terms, right, and I look at this, it looks like this is converging to -1. Okay. So if I look at the subsequence of odd terms, right, they are converging to -1. If I look at the even terms, I see that they are converging to 1. So this sequence is bounded. It's bounded because if I look at the absolute value here, okay, that'll just go away because this is just changing the sign. This piece is bounded by 1, bounded above by 1, because the numerator is always smaller than the denominator. So this whole sequence is always bounded by 1 in absolute values. It does not converge, but it does have subsequences that converge. Okay. Now, so far it's been easy to sort of pick out these convergent subsequences because you can just look at odd versus even terms. But notice, for example, if I came up here and changed this to, something like a sine of n, now it's going to be really hard. This is still bounded because, again, this is still bounded in absolute values by 1. This is still bounded. But if I try to write out terms, first of all, they're not going to come out nearly as nicely as these did. But it's going to be very difficult to pick out what some convergent subsequence is. So probably I don't want to try to prove this by saying, oh, here's exactly how you select the subsequence. I probably want to take a more general approach. So what we are going to do is we're going to first sort of prove this modified version. Now, this is still sometimes referred to as the Bolzano-Weierstrass theorem, but we'll see that in a bit that this implies the other thing that we want. So I want to first prove that every bounded infinite set of real numbers has an accumulation point. Okay. Now there's actually sort of a slick proof of this, and it goes back to some of the compactness stuff we talked about, I think, back in lecture 9. So if I wanted to prove this, okay, we're going to, again, go back and appeal to some of that compactness stuff. So let's give a name to my set. So let E be a bounded infinite set. Since E is bounded, there exists some real number M, positive real number. So I'll write it that way. Okay. There exists some positive real number such that the set E is a subset of the interval from minus M, the closed interval from minus M to M. Okay. Recall, so this is that compactness bit. So recall that the closed and bounded interval minus M to M, right? Any closed and bounded set is also compact. That's called the Heine-Borel theorem. So recall that this is compact. All right, now we've got all our setup here, and now we're going to run like a mini proof by contradiction. Okay, so suppose toward contradiction that minus M to M contains no limit points of E. Okay. So suppose there aren't any limit points in this set. Well then, what can we say? Um, then the set V sub little m, which I want to define to be, oh, sorry, I don't want to define that yet. I want to, sorry. Then for each little m n minus m to m, we may construct a set V sub little m such that V sub m is an open neighborhood of the point little m, and V sub m contains at most one point of E. All right, so let's explain what we're sort of doing here. So you have this set E. Let's draw a picture. So you have this set of real numbers. You have this set E. Maybe it's sort of a whole bunch of points. I don't know. Maybe it contains a little interval here, like well, whatever this set E sort of looks like. But it's bounded, so you've sort of blocked it in, between this minus m to m. All right. So the idea is that I am going to go around and at each point in m, if, because I'm supposing towards contradiction that it doesn't contain any limit points of E, since it doesn't contain any limit points of E, then I ought to be able to come here at each point and construct a little neighborhood of that point that doesn't contain any other points of E, except it is possible, like right here, if the point that I select in my interval minus m happens to be a point in E, then of course this little neighborhood of that point is going to contain one point of E. But because I'm assuming this doesn't have any limit points of E, then the points of E it does contain are isolated points. So I can put a neighborhood around them that doesn't contain any other points of E. So I ought to be able to, at every point, put a little open neighborhood of M, which I'm calling V sub M, such that that set contains at most one point of E. And that one point is just the point M if M is in E. If M is not in the set E, then V sub M doesn't contain any points of E. All right. So now note that the collection of sets V sub M for each M in minus M to M forms an open cover of minus M to M. Why? Well, V sub M has to cover up each point because each of these intervals covers up the point M. And you're doing that for every M in minus M to M. Okay, so certainly this is an open cover of that interval. But now, since this is compact, there must exist a finite subcover. All right, now here's the problem. So you now have a finite collection of these V sub M's that cover up all of M. but M also contains all of E. Okay. This finite collection, each of the V sub m's contained at most one point of E. Okay. So since each V sub m contains at most one point of E, E then must be finite. Right? Because now I've been able to cover this whole interval from minus m to m with finitely many of the V sub m's. Each of those V sub m's only contains at most one point of E, so there must only be finitely many points in E. But this is a contradiction since we assumed that E is infinite. So this is a contradiction. And hence, there is E has a limit point. And in fact, that limit point must be in this set minus m to m, but that's not, we didn't need to prove where it was. We just needed to prove that it has a limit point or an accumulation point. Okay, so this property here, and we actually mentioned this back in the compactness video, the existence of this limit point or this accumulation point is really sort of equivalent here to the compactness, right? So every bounded and infinite set of real numbers has an accumulation point. Now, again, all of this are related to properties of the real numbers. So if you're working in other metric spaces, these proofs do not always work because, again, the real numbers have nice properties that not all other metric spaces have, right? Namely, it's what we call a complete metric space. So again, this doesn't always work, but it does work in this case. Now, once we have this, okay, how does this relate then to this other idea I was talking about bounded sequences having convergent subsequences? Well, now let's sort of string together a couple of theorems. Okay. So I claim then that now if I take this should then imply that every bounded sequence has a convergent subsequence. Okay. So how do we get from this then to this? All right. So the idea here is that we ought to again, so we're going to let E again be, so take our set AN, or sorry, our sequence AN, and just take the set of values. Okay, sort of the range of the sequence in a way. All right, if E is finite, well, okay, what would that mean? I've got this infinite sequence, right? But what if I only have finitely many outputs? Well, that means that at least one output has to be repeated infinitely many times. So if E is finite, there exists some value, we'll call it A, in my set E, and a sequence in sub K, such that a sub n sub 1 is equal to a sub n sub 2 is equal to, right? Basically, if my set E is finite, there's some value A that's repeated infinitely many times in my sequence. That's the only way I could have gone from this infinite sequence to this finite range, okay? Well, if that's the case, then A sub n sub k converges to A, and we're done, okay? So if this set E is finite, then it's going to be, there's going to be some constant sequence that I can just pull out as my, or some constant subsequence I can pull out of my sequence to form my convergent subsequence. All right, what if E is infinite? Well, now if E is infinite, I should be able to apply this, right? Because now I have a bounded infinite set of real numbers, okay? And I know that this has an accumulation point. So if E is infinite, then E has an accumulation point. Okay. And in that case, I can choose a sequence. I'm going to choose n sub k. Oh, sorry. Let's give this accumulation point a name. We're going to call it A. Then I'm going to choose n sub k so that A sub n sub k minus A is less than 1 over k for each k. Okay. So the idea is if I have an accumulation point, there's got to be some point in my set that's within distance 1 of that. So go in your sequence and find the first value that is within distance 1. Then go in your sequence, find the one that's within distance 1/2. And there's got to be something within distance a third and a fourth and a fifth. And you do this over and over and over again. And then this sequence A sub n sub k converges to A. So this theorem that we've written down here really does imply that every bounded sequence has a convergent subsequence. So this property that every bounded infinite set of real numbers has an accumulation point, that's helpful in a very abstract sense when you're working with lots of different kinds of objects. When in particular we're talking about sequences, this implies that every bounded sequence has a convergent subsequence. All right. Now, all of these theorems, again, have really, these are theorems about convergence, right? And what we want to do now is we want to actually add on one additional property of sequences. Well, once we add on that property, then we'll want to see how does that, how does that relate to all of these other properties that we've seen. Okay. So the property that we're going to add on is going to be what it means for a sequence to be Cauchy. Now, Cauchy is the name of a mathematician, so it gets its name from the mathematician Cauchy. It's not some other, it doesn't have any other meaning. It's just somebody's name. And a Cauchy sequence, we say a sequence is a Cauchy sequence if for every epsilon greater than 0, there exists a natural number capital N such that a sub n minus a sub m in absolute values is less than epsilon whenever little n and little m are both greater than capital N. Now, this looks in a lot of ways similar to the definition of convergent, right? What it means for a sequence to be convergent. But notice here we've replaced the L with a sub m and we're looking at what happens when little n and little m get greater than n. So if we go back to convergent, what does convergent mean? Convergent means that if you go far enough out in your sequence values are all getting close to some fixed value L. So L is a fixed number, and your sequence converges to L if, as you go far enough out in your sequence, past capital N, you can get within epsilon of L for any epsilon. Now here, what this is saying is if you go far enough out in your sequence, it's not saying necessarily that you get close to some fixed value. What it's saying is your sequence of values get close to each other. So it's saying if you go far enough out in your sequence, then all of your sequence values are going to be within epsilon of each other, right? Now, that's a little bit different, right? In one case, I'm saying that sequence values get close to each other. Or sorry, in one case, I'm saying sequence values get close to a fixed value. And in the other case, I'm saying the sequence values all get close to each other. But it sort of naturally raises the question, well, maybe like, I don't know, like maybe they one implies the other, maybe they're equivalent. Like I don't know. They're sort of the same, but sort of different at the same time. And so what we want to do is explore the relationship between those. Now, you can actually fairly quickly prove things. So again, if you go back in and we sort of before, we had bounded, monotone, convergent, and then we've added this Cauchy thing. So if you go through, you might, we already knew that convergent implied bounded, and you'll actually, in almost the same way that you can prove convergent implies bounded, you can prove that Cauchy implies bounded. And so again, it makes you start to think like these seem to be behaving fairly similarly. Maybe they are equivalent to one another. Okay. And so it actually turns out that indeed they are equivalent. And so what we want to do in the remainder of this video is explore that equivalence just a bit. So a sequence of real numbers is Cauchy if and only if it is convergent. Okay. Now, one of these directions, okay, so proving that if it's convergent, it must be Cauchy, that is actually a fairly straightforward proof. If you think about it, if all of your values are getting as close as you would like to L, then they all must be getting relatively close to each other, right? Because they're all close to this fixed thing, right? So it's sort of like telling you, oh yeah, I'm close to I'm close to the bell tower on campus. You're close to the bell tower on campus. We must be close to each other. Okay. In the other direction, again, it's a little harder because it's almost like saying, well, we're close to each other. So is there some fixed thing that we are both close to? It's a little harder. Okay. So we'll actually prove this if and only if by proving both directions. The first direction we'll prove is that if it converges, then it is Cauchy. So this is sort of the reverse direction. Okay. So assume that AN converges to L. Okay. And let epsilon greater than 0 be given. Okay. Well, since AN converges to L, there exists a natural number, capital N, such that I can make AN minus L as small as I would like. But, I don't know exactly how small I need to make this yet. So let me leave some room there. Whenever little n is greater than capital N. All right, but now I want to prove that this thing is Cauchy. So, sorry, not choose. Let or if, let's say if little n and little m are greater than capital N, then what's this difference look like? Well, I want to show they're close to each other. I know they're both close to L. So let me express this right in terms of their distance to L, because I know something about their distance to L. And so applying triangle inequality and some properties of absolute values, I get this. But now I can make each of these as small as I would like, right? I can make it less than whatever I put in this green box because n is greater than capital N and little m is greater than capital N. So these are both little n and little m both satisfy this condition. So this difference must be less than whatever's in the green box. So what if in the green box here, if I put epsilon over 2 here, then I'll get this is less than epsilon over 2 plus epsilon over 2, which is epsilon. Okay. And so I've shown that if AN converges to L, then I found my capital N such that if little n and little m are greater than capital N, then this difference is less than epsilon. Okay. Now, just briefly, let me remark here that if you're working in a general metric space, so you just have some way of measuring distance, you can repeat this proof. Okay. And so it actually turns out that in any metric space, a convergent sequence will be Cauchy. The reverse implication does not always hold. Okay. We need sort of additional properties. Okay. So let's briefly look at the opposite direction. So now I want to show that Cauchy implies convergent. Okay. So let AN be a Cauchy sequence. Okay. We mentioned, although we haven't proven it, that means it's bounded. Okay, so Cauchy implies bounded. Again, the proof is very similar to convergent implies bounded. Okay, and then by the Bolzano-Weierstrass theorem, there exists a subsequence A sub n sub k converging to some point, let's just call it A. Yeah. Now, what I want to do is I want to show that if this subsequence converges to A, then since my sequence is Cauchy, it actually has to converge to A as well. Okay. So what I'm going to do, changing colors here. So I'm going to choose a natural number capital N such that whenever n sub k is greater than that capital N, A sub n sub k minus A in absolute values. I can make that as small as I want. Let me make that less than epsilon over 2. Okay, of course, I'm now realizing I forgot up here, right? I need to let epsilon greater than 0 be given. Okay, I've joked before that analysts should just have a stamp. So you can just stamp that on the start of most of your proofs. Okay. But I can make this difference as small as I would like because this subsequence converges here. Okay. Now, okay, what's my goal? My goal is to show that this whole sequence has to be convergent. Okay, so if I choose a little n greater than capital N, oh, sorry, one more thing. I also need to write down what it means to be Cauchy here. So since AN is Cauchy, there exists, now I'm going to have a couple of n's here, so let's call this n1. Okay, so there exists a natural number n sub 2 such that whenever n and m are greater than n2, I can make this difference as small as I would like. And I'm going to want to make this less than epsilon over 2 as well. All right, now I'm going to set n to be the larger of n1 and n2. Now, if little n is greater than capital N, then what do I get? So a sub n minus, a sub n minus a, and that's what I'm converging to. Okay. So what I can do is I can express this as a sub n minus a sub n sub k plus 1 plus a sub n sub k plus 1 minus a. Okay. I can then apply triangle inequality. Okay. Now, because both of these values are bigger than n, okay, then this quantity will be less than epsilon over 2. Because this subsequence converges to A, this will be less than epsilon over 2, and I get that the whole thing is less than epsilon. Okay. So what I have here then is that this Cauchy sequence must be convergent. Now, this does not work in just a general metric space, and really the reason comes down to our use here of this theorem. This Bolzano-Weierstrass theorem. So again, the fact that this exists is actually equivalent to a more powerful theorem that doesn't hold in any general metric space. So in general, if you have any sort of convergent sequence, it must be Cauchy. It is not necessarily the case that any Cauchy sequence is convergent. In fact, we have a special name for spaces where all Cauchy sequences are convergent. Those are called complete metric spaces. And again, that goes back to that completeness axiom, right? That that every non-empty bounded set has a supremum, right? So again, there's some very deep structure going on in the real numbers that allows a lot of these theorems to be true. Some of them are true for general metric spaces. Others of them are special and are really due to the fact that the real numbers have this completeness property. So that will conclude our discussion of just sequences of real numbers. And in the next video, we'll begin discussing series of real numbers and determining whether they converge or not.